So now we're going to take a look at the conditions for differentiability of a function at a particular point. And so we say that f is differentiable at a point A if f is continuous at A and if there are no sharp turns at that given point. And so the conditions for a function actually be differentiable. And so what differentiability means is just it has a derivative that is properly defined at that given point, at point A. In order for our derivative to be properly defined, we must be continuous at that point, and we delved into the definition of continuity in our limits playlist, and there must be no sharp turns at that point. And so what do we mean by sharp turns? I mean, this is kind of just, a very informal definition, sharp turns. But I'm going to actually give us a couple of examples to illustrate what I mean by that. So a sharp turn, and we're going to actually take a look at this first example over here. This function looks kind of, it's continuous, right? This is a continuous function. But there is a particular point at which it's not differentiable. And that particular point is right over here. So I'm going to highlight that. It's at this point. We don't really care about what its value is right now. But the reason why it's not differentiable at this point is because we have what looks to be a sharp turn. And how are we able to kind of determine whether or not this is a sharp turn? Well, let's think about it. What would the tangent line look like at this point? Well, I mean, it looks like a minimum value or kind of like a local minimum. So maybe it would be a flat sort of, horizontal line. But we could also argue that, we instantly switch to this linear function over here. So maybe the slope of the tangent, or maybe the tangent line would kind of just look like that linear function, something like that. But then we could also argue that right before we reach this point, it seems like we're decreasing, so maybe our tangent line will look something like that. And so the thing is, we have a bunch of different sort of valid tangent lines, and so we don't necessarily have one unique tangent line at this point. And you could also argue that maybe it's a vertical tangent, maybe it'll look something like that. And so the thing is, we don't necessarily have one proper definition of a tangent line at this given point because of the fact that it's a sharp turn, because I mean, it looks like we're kind of just decreasing and then we stop and we just very sharply increase. It's not sort of like a smooth curve that starts increasing again. So because of the fact that it's a sharp turn, we say that we aren't differentiable at this given point, but we're differentiable, from what it looks, it seems as though we're differentiable everywhere else. And so over here we have another example. We'd say that this function is differentiable everywhere except for this particular point because at this point we have a discontinuity, right? We have a jump discontinuity. And the reason why we're not differentiable if we aren't continuous is because of the fact that, again, what would the tangent line look like at this point? Would it be something like that? Would it be something like this? We don't really know. And then again, over here, at this particular point, we kind of jump. We have a discontinuity, so we don't really have a proper definition of what our tangent line would look like at this point, so we can say that we are not differentiable at this particular point. But we are continuous, and it looks like there aren't really any sharp turns anywhere else, and so we could say that maybe we are differentiable everywhere else. And that's a pretty interesting thing, is that, differentiability implies continuity, but continuity does not necessarily imply differentiability, as we saw with this particular example right over here. And so it isn't necessarily like a double implication. And then over here we have this function. It looks to be kind of just a smooth curve with no sharp turns, and it looks to be continuous everywhere. And so because of the fact that we meet both conditions for every point, we can say that this is going to be differentiable over R. So we're just going to be differentiable over the real numbers because there is no discontinuities, and it seems like we don't really have any sharp turns, which would kind of mess up our proper definition of the tangent line at that given point. And so we are differentiable over R. And then finally, let's take a look at the actually an equation of a function. So we have this rational function over here, f of x, and just from visually inspecting it, or just from visually inspecting the equation, we can say that we are not differentiable, I don't feel like writing the whole word out, at x equals -1. Why? Because we aren't continuous, because we're not continuous at this particular point over here, right? Because if we were to input f of -1, then we would be dividing by 0, and so we aren't going to be continuous at this point. And so we could say that we are differentiable at everywhere except for x equals -1, because, rational functions generally will be sort of smooth curves except for wherever they have asymptotes, so we won't really have any sharp turns, but we aren't continuous at x equals -1, so we can say that we aren't differentiable at that point. And so the point is, we just need to take a look at two conditions in order to determine whether or not our function is differentiable at a point, and that's first of all if it's continuous at that point and if there aren't really any sharp turns.